All right, so the first one asked is which one's logistic? Remember, a logistic equation looks like dy dt is equal to ky L minus y. It may also be written like ky 1 minus y over L, and it may also look like kyl minus ky squared. But what you're looking at is whatever the variable is up here that it's changing, you have to make sure you have a product of those. So this one does not have a minus sign, so it's not this. This one says dr dt, so I should have an r here and an r here. And right here we have dq, and we have a q here and a q here, so it's going to be this one. Let's double check. This one has a w and w squared, so that's not it. Now remember, with logistics, we also know a lot of things about it. This L right here is the carrying capacity. We know if you look at the general graph, the carrying capacity is what it's heading to. At half the carrying capacity, it changes concavity. So if you start below half the carrying capacity, it increases and is concave up, and then increases and is concave down. If you start above half the carrying capacity, it's increasing but concave down. If you start above the carrying capacity, then it's going to decrease and it's concave up. Which of the following equations is not separable? Separable means I can get my x, all my x's on one side and all my y's on one side. So looking at the first one, if I factor out an x, then we can separate that. So it's not that. Part B, number B. So if you can think of, instead of subtracting those things, you would have e to the x times e to the negative 2y, because when you multiply things with the same base, you add them. And now you can see that it's a multiplication between them, so we can definitely separate that. C, I don't think I can separate that because it has to be a product of y's and x's. And then here you can see you can already separate this one by pulling our y plus 1, multiplying it over there. So C is the one that is not a separable differential equation. So this is asking for Euler's equation, Euler's method, which of the following gives the correct first setup for the first step of Euler's method? So we want to do 2 equal step sizes, and we're starting at here. So our x value is starting at 2, and we're heading our x value to 1. So halfway in between is 1.5, which means our step size is going down. And then using our first step, remember that's going to be y1 is equal to y0 plus h, following the slope field. So y0 is 3, h is negative 0.5, and my first derivative at 2, 3. So our first derivative at the value 2, 3 is 2 plus 2 times 3, which is 6, is 8. So our next value is, let's see, y1 would be, let's see, negative 4 plus 3, so oh, which one is the right one? So this one's the right answer. Sorry, I didn't even need to crunch it. It's right there. So the first thing I look at with this slope field is that at y equals x, we have a horizontal horizontal line, horizontal slope, so slope would be equal to 0. And you see right here, if y is equal to x, the slope is definitely going to be equal to 0. If y is equal to x, on B, it's definitely going to be equal to 0. If y is equal to x, this is not going to be equal to 0, nor is this one. So I'm between these two values. So I'm going to pick values in different quadrants and see how they behave. So if I pick the value 1, 0, our slope should be positive, because that would be right here. So if I put 1, 0 into the first one, so dy dx 1, 0 would be 0 minus 1, which would be negative which means I should have a negative slope, and that's not true, so it's not this one, so it has to be B. A hilarious meme about Brian and Tony is spreading through the AP Calculus students. The number of students that have seen the meme follows a logistic curve. The number of students that have seen the meme is increasing at 125 students per day when S reaches half the carrying capacity of 5,000 students. So we know our carrying capacity is 5,000 students, so I know it's not B or C. 5,000 students, the carrying capacity is either going to look like this or like this. So we know dsdt when S is half the carrying capacity is 125. So that means if I plug in the population of 2,500, I should get dsdt is equal to 125. So looking at the first one, is 125 equal to 1/10 times 250, 2,500, and then 1 minus a half. So looking at that, that's going to be 250 times a half, which is that, exactly that. Next one is solving for the differential equation. It is not separated yet, so the first thing I'm going to do is separate it. So integrating the left is a natural log. Integrating the right, that's really x to the negative 2. So we know that y is going to be equal to c e to the negative 1x, and that's going to be big C. So our answer would look like C. This is a solution to which of the following differential equations? So remember, if it's a solution, when you plug it in, it works. For example, x plus 1 is equal to 5. X equals 2 is not a solution because when I plug it in there, I get 2 plus 1 is equal to 5. That's not true. But x equals 4 is a solution because 4 plus 1 is equal to 5. I don't know how to solve this differential equation, but I can take the solution and plug it in there and see if it works. Okay, so first thing, all of these have the first and second derivative. So I'm going to go through and I'm going to do it on the top over there so I have a little bit more room. So here is y. Y is going to be e to the 2x plus cosine x. So then y prime is equal to 2e to the 2x minus sine x. Y double prime is going to be 4e to the 2x minus cosine x. So I'm going to try to plug it in here first. So that would say 4e to the 2x minus cosine x minus the y value plus 2 times cosine x. Is that equal to 0? Right here I've got cosine x minus cosine x, so this and this and this cancel, but 4e to the 2x minus e to the 2x is not going to cancel, so it's not A. We'll go to the next one, which is B. So looking at B, y double prime is 4e to the 2x minus cosine x minus 4 times y is this equal to 0? So minus 1, minus 4, which gives me minus 5, plus 3, we're still going to have a cosine left over, so it's not that one. And I'm going to go ahead and try D. Minus 4 times y plus 5 cosine x. So this is 5 minus 4 minus 1, so all of our cosines cancel. And then looking here, 4e to the 2x minus 4e to the 2x, those all cancel. So we got 0 is equal to 0, so that is your solution. Okay, so we have a logistic equation. Again, you're looking at that product of m. You should have m minus m squared. So first thing we need to do is get it in the correct situation so we can find what the carrying capacity is. What I would prefer to see is something that looks like this, Km L minus m, and this right here would then be your carrying capacity. So the first thing I'm going to do is kind of write this, instead of writing 0.01, I'm going to write this 1 over 100. So then I'm going to factor out 1 over 100 m. So we're going to be left with 300 minus m. So we can see right now that our carrying capacity is in fact 300. We know that it'll grow the fastest at half the carrying capacity. It does not give us our initial condition, but if our initial condition started below half the carrying capacity, it would increase at an increasing rate until that point, and then it would increase at a decreasing rate. If it was above half the carrying capacity, it would increase at a decreasing rate. And if it starts above the carrying capacity, it's going to decrease at an increasing rate. Okay, so looking, if m is bigger than or equal to 300, the population of meerkats are decreasing. That's true. If your initial condition is above the carrying capacity, it's going to be decreasing. The rate at which the meerkat population is growing the fastest is at 150. Again, true. That is half the carrying capacity. The limit as t goes to infinity of m at t is equal to 300. Again, that's true. They're going to be heading to their carrying capacity. So all three. So here we want to look at this differential equation, and we want to use Eulers' method starting at x equals 4 to approximate x equals 3. So x0 is equal to 4, and we want to approximate x of 3. So right here in between is going to be 3.5. So we know our step size is 0.5. So y of 0, so when x is equal to 4, y is equal to 1. So what we really want is the answer right there. So y1 is equal to y0 plus h f prime at x0, y0. So y0 is 1. Our step size is negative because it's going backwards. And then we're going to use this value to find our slope. So at x equals 4, our slope is 6. So negative 3 plus 1. So our next guess is negative 2. And we do this again. So y2 is equal to negative 2 plus h. And this time we're going to plug in 3.5 into our differential equation, and we get the value of 5. So that's negative 2.5. So negative 4.5. Okay, so we have a differential equation. We have an initial condition. First thing they want is our slope field. So all we're doing is plugging in the points. So here we have dy dx is going to be equal to x squared minus 4y. We have different points they want us to do. The first one is 0, 0. Plugging in 0, 0, we're going to get the slope of 0. Here, this is 0, 1. So dy dx at the point 0, 1 is negative 4. So it's going to be very steep down. Right here, we have dy dx at the point 2, 1. So that would be 4 minus 4. So the slope again is going to be 0 right there. Over here, we're going to find dy dx at the point 2, 0, which would be 4. So a positive 4 slope there. Right here, we're going to have dy dx at the point 2, negative 1, which is going to be 4 plus 4. So this is going to be even steeper. And the last one we need to find is this one right here. So dy dx at the point 0, negative 1 is positive 4. So like that. These should have the same slope. Part B. Let k equal f of x minus 3x plus 6. Does k have a local minimum, local maximum, or neither at x equals 2? All right, so if we want to know if it has a local maximum or minimum, the first thing we have to do is take its derivative and find its critical point. So k prime is going to equal to f prime minus 3. We want to know when this is equal to 0. F prime is equal to this, so we want to know when x squared minus 4y minus 3 is equal to 0. We were looking at the point 2, so k prime at the value 2 is going to be 4 minus at 2, the y value is 1. So this is not equal to 0, which means k of x does not have a critical point at. Has no critical point at x equals 2, or t equals 2, x equals 2. So therefore, x equals 2 is not a relative max or min. Find the value of this. Okay, so let's see. I'm guessing as we plug it in, we're probably going to get 0 over 0, but we should probably verify that first. So looking at the top, the limit as x goes to 4 of 3e to the 12 minus 8 minus the integral from 1 to 4 of x e to the x dt. So looking at this is by parts. So on the derivative side, we're going to have x. On the integral side, we have everything else. Copy down the diagonal. So we're going to have 3e to the 4th minus x e to the x minus e to the x. And we're going to evaluate from 1 to 4. So 3e to the 4th is going to be that equal to 4e to the 4th minus e to the 4th minus the quantity 1e to the 1 minus e to the 1. So this is equal to 0. This is 3e to the 4th, 3e to the 4th. So in fact, this is equal to 0. Now again, let's look at the bottom now. So the limit as x approaches 4. So we're now going to do Eulers method with the exact same thing. So now we have x0 is going to be 2, and they want us to find x sub 2, which is equal to 1. Notice again, our step size is negative. Y of 0, we already know is 1. Remember that our differential equation is, in fact, x squared minus 4y. So y1 is going to be y0 plus h, and we're going to be plugging this into our differential equation. So 4 minus 4, this is equal to 1. Then we're going to do it again. Y2 is equal to 1 plus the step size. And this time we're plugging these guys into our differential equation. So 1.5 squared. And then minus 4 times 1. And this works out to be 1.875. And that's your Euler's approximation. Back to a logistic, it wants to know which one of these could be the logistic equation above. Remember, logistic is a product of m's. You want to look, or p's, whatever, if it's dp dt, you want to look for either k p l minus p, or dp dt is equal to k p 1 minus p over l. Or lastly, it could look like dp dt is equal to kp minus kp squared over l. So you need that minus p squared in there. This does not even have a quadratic. This one has the minus p squared. So does this one. This one's got a plus p squared or m squared, so that's not it. So now we have to differentiate between the two. Notice here our carrying capacity is 240. This is one that has 240. This is not the carrying capacity. That's a carrying capacity of 120. So the answer is C. Here we have a separable differential equation. So 2y dy is equal to 3x squared dx. Integrate both sides. So y squared is equal to x cubed plus c. We can now use our initial condition. So 9 is, and then 8 plus c, so c is equal to 1. So our equation would be y squared is equal to x cubed plus 1. Solving for y, we take the square root of both sides and we'd get a. So we have another Eulers method. So they give us our initial condition here, and they want us to find f of 2. Remember, Euler's method is always 2 steps. My initial condition is 1, negative 2. We want us to find 2, so this time our step size is positive. So y1 is equal to y0 plus the step size. And this time we're plugging 1, negative 2 into the differential equation. So this would be negative 4 divided by negative 2, or 2. So our next step is negative 1. And we do it again. So y2 is equal to y1 plus the step size. We're plugging these guys into our differential equation. So 2 times 1.5 is 3, minus 6 is negative 3 over negative 1, which would be 3. So half of 3 is 1.5. So this is going to be equal to a half. G is equal to f of 2x minus x squared. The slope field for dy dx is given above. Find g prime of 2. Okay, so g of x is equal to f of 2x minus x squared. So g prime of x is equal to f prime times the chain rule, derivative of the inside. And now we're going to plug in 2. So it'll be f prime is 0, and plugging 2 times negative 2. F prime is 0 looks like it's negative 1, so 2. Solve this differential equation. Okay, so first thing, this is a pretty bad differential equation because when we separate it, we now have to do partial fraction decomposition. So going up here, we're going to decompose those fractions. So if x is equal to negative 2, we're going to get b is equal to negative 1. If x is equal to negative 1, we're going to get a is equal to 1. So integrating all of that, you're going to get the natural log of x plus 1 minus the natural log of x plus 2 plus c. So I know if I start combining it, I'm going to have possibly not this one, because that's going to be the wrong signs. Same here, I don't have this 2 out in front, so that's not going to be right. Now we can use our initial conditions to find c. So y of 0 is going to be 3 minus the natural log of 2, which is going to be the natural log of 1 minus the natural log of 2 plus c. So natural log of 1 is 0. So we're going to get that c is equal to 3. So looking at that, the answer must be A. Consider the logistic. We know y of 7 is equal to 100. At x equals 10, which of the following is true? Well, we're still below half the carrying capacity, so we know we're increasing at an increasing rate. So let's see, let me double check. Y of 7, so right here, we know our carrying capacity over here is 50. We know at 25 it's going to change. Y of 7 is equal to 100. So actually we're above over here. So we're going to be decreasing and concave up because that's where our initial condition is, above half the carrying capacity. And this one works out to be B. And then lastly, C is 80. You can see right here, there's the carrying capacity.